You mean ungood. Or ungood.
Jenna's having lots of unfun.
It's not having unfun.
Hold on.
What is going on?
I need to add a little bit more volume to this.
Oh yeah. Oh, I do remember this book. Is there something on the bigger read?
I think there's like volume on the video.
Yeah, go down to the bottom.
Like, oh, it's on.
It's already maxed out.
Oh, it'd be on the speaker then.
Close to first in this world. Sorry. There's our first in this world right there. Now we have to.
You know they had fun making us do it.
I like how he was on the nose.
But all you can't.
Oh, no, this is for the cat. No. I hate this thing.
For all your cat fans.
Ew.
You know who this is? You know Leonard? Leonard from the Big Bang Theory?
Wait, who is it?
That's Leonard from the Big Bang Theory.
Oh no, what's really funny? Why everybody says like smoke.
That's Leonard from The Big Bang Theory.
That is Leonard. I never knew that.
Never did neither.
Ron Sheldon.
I know.
So there's our humor about friction. I watched it last night for like the 20th time. I thought, you know what? We're talking about friction.
Why not?
And going into the frictionless world. Clark W. Griswold came close to the frictionless world there.
We should add some of the.
The slip wax.
Yeah, the sled wax to the bottom of our.
I love that movie.
Imagine putting slip wax on your shoes.
All right, let's take a look at, once again, an inclined plane. And what occurs with an inclined plane. Okay, we have, to start motion, we have to break what?
Friction.
Which friction?
What?
Inertia.
There's two different frictions. There's sliding friction, static friction. Static friction. So if I touch this, I need to be able to break my static friction somehow. Well, it doesn't move once I touch it, so I haven't broke my static friction. But once I get to a point of this angle right here, I break my static friction. So at this angle right here, I slide down pretty much at a constant velocity. So let's look what its curves. I'm going to throw the idea of sliding friction here. We have our force perpendicular and our force parallel. And what we talked about before, this is our force normal. And this is our force of gravity here. Our force parallel is our force of gravity sine of theta. This angle here, theta, is this angle theta here. Okay, we're just going back over. My force normal is force of gravity times the cosine of theta. Now, if I tap this to break static friction, and I gain a constant velocity going down, I tap it to break static friction, and I go down at a nice leisurely pace going down. Once I tap and break static friction, no, I don't want to do that break. There we go, let's try that break. I'm sorry, I'm a math teacher.
It's fine, it's fine.
Who's judging me?
I totally understand.
What?
If I don't have squiggles underneath, I'm no good anymore. If I can't get squiggles underneath my typing, I'm not very good. If I break the static friction, and break static and slide at a constant velocity down the plane. If I'm sliding at a constant velocity, what is true about acceleration? There is none. So this tells me here my acceleration is equal to 0. Well, if we then take a look at our force net, is equal to mass times acceleration. What's our force net? 0. Because this is a value of 0. That means my force net is a value of 0 newtons. When we have key phrases here. We have 3 key phrases. We have acceleration equals 0, velocity is a constant, force net is equal to 0. These 3 things go hand in hand. When you say you have a constant velocity, that means the acceleration is equal to 0 and your net force is equal to 0. If you say your net force is equal to 0, that means you have a 0 acceleration and then you have a constant velocity. If you say you have a constant velocity, that means acceleration is equal to 0, force net is equal to 0. These 3 things are connected together. When you say one, you have the other. Well, how are we going to calculate our force net here? Well, we have our force of friction, and we also have our force parallel. Well, our force net is equal to our force parallel plus our force of friction. We have no applied force here. We have no applied force. Well, our force parallel is equal to Fg sine of theta. Our force of friction is equal to the negative Fg cosine of theta. And then force net is equal to 0. Which now allows us to solve, if I add my Fg cosine of theta to the other side, we have Fg cosine of theta is equal to, hold on a second. I guess we should multiply this by mu, because that would be our force of friction. This will equal Fg sine of theta. Sorry about that. If we would divide both sides by Fg cosine of theta, the Fg's would cancel out. Leaving us with mu is equal to sine theta over cosine of theta. Sine over cosine is equal to theta. So when I can brake and slide down at a constant velocity, I can get my coefficient of sliding friction is equal to the tangent of theta. The angle here.
Well, I mean, the, like, once the heat is down.
Now, if you have a force applied, that's not going to affect. That's going to be a little bit different. Okay, because all of a sudden we have a force being applied there. If we don't have a constant velocity, okay, this does not work because we don't have acceleration equals 0. Okay, if we don't have a constant velocity, this does not work. But if I can slide this down, if I can break my static friction, and slide this down at a velocity that is a constant velocity, my angle there is 13.4 degrees. 13.4 degrees. So my coefficient of sliding friction then would be the tangent of 13.4 degrees. Let's see here. Need to throw some degrees in here. Or, all right. Nah, because I have force being applied here.
How's it going?
Let's throw my angle to be all 15 degrees. Which direction is the masses moving? Which direction is the masses moving? To begin with. Now, hopefully you can think, yeah, I got 10 kilograms, I got 5 kilograms there, and you're at an angle, you're probably going to be able to assume which direction we're going to be going. But you can mathematically verify that by looking at your force parallel and your force applied, and your force of friction. So calculate your force parallel, force perpendicular, which is your force normal. Yes, Mrs. We went through some like W. Griswold and almost.
I saw, I heard you guys laughing, I popped in here, I saw what you were doing, that's pretty cool.
Living in the frictionless world.
That is good. There had to be some friction, because the bottom of that thing was,
Well, once you got
once you got onto the road, yeah.
once you got on the cement, there was fire coming up.
What did you
Little
do?
heat
You did
there.
something at work that he sprayed on it?
Yeah.
Yeah. That's a good video to go with friction. Right there.
So find your force parallel, force perpendicular. What's your force parallel, Isaac?
12.7.
0.7 newtons. Force perpendicular,
47.4.
newtons. Our force applied, 98.1 newtons. Which once again, we are pulling on it here, which pulls it down, which pulls it up. And we have force parallel, which is pulling it downwards at 12.7 newtons. So I think our assumption of this is going to be going up the plane is a good assumption. Which then tells us what's going to happen to our force of friction. If we have motion going up the plane, that means our force of friction is going against, it's resisting motion. We will resist the motion. Our force of friction, Todd, is equal to what? So our force of friction is 4.74 newtons. So if we take a look, I always look at positives and negatives. Whatever direction our motion is what I typically put as a positive motion, a direction. So we have 98.1 newtons that's pulling it up the plane. So when we're calculating our force net, we have a force applied plus our force of friction plus our force parallel. My force applied is going to give me my motion up the plane. Our force of friction is resisting that, so we throw a negative with that. And our force parallel is trying to pull it down the plane, so I'm going to go negative with that. You get your force net, Jack?
3.66 newtons.
What we want to do is calculate the acceleration of the masses. Force net is also equal to mass times acceleration. So we have 80.66 newtons is equal to our mass. What we're going to use for the mass here? 15 newtons, or 15 kilograms. Because we have two masses that are here. Both of the masses are moving. So we can divide by 15, divide by 15. Acceleration then comes down to what value, Justin?
5.38 meters per second. Correct.
Not really.
Let's see here. A 420 gram mass to move up the plane, it takes 420 grams, 420 grams to move the block up the plane at a constant velocity when it is tapped from behind. We want to calculate the coefficient of sliding friction. So if we take a look here, we have our force of gravity. What we have to watch out for is we are in grams. So converting this into kilograms, we have 123.22. We have 420 grams times our 9.81 for our force being applied. Once again, we are moving at a constant velocity. Key thing to remember here, our force of gravity. What do we get for a force of gravity, Cal? Over here.
2.15 newtons.
And our force applied.
4.12 newtons.
Are we good with those? Once again, we can find, we don't know a theta there, but we have 215 sine of theta and 215 cosine of theta. If we're moving at a constant velocity, that means acceleration is equal to 0. Our force net is also equal to 0. Our force net is equal to force applied plus our force of friction plus our force parallel. But we know this is equal to a value of 0. Our force applied is 4.12 newtons. Our force of friction is negative 2.15 cosine theta times mu. Our force parallel is negative 2.15 sine of theta, and this is equal to 0. Problem we have is we have two unknowns. We have theta and we have mu. But can we find theta?
Use the time.
10 to 1, which is what? Trig function. Sine of theta. The sine of theta is equal to what over what?
Oh, wait a minute. No. Lost the 10.
So we have to change 1 to meters or 1 to centimeters. Does not matter which one. I like 100, 10 centimeters over 100 centimeters. Or I'm sorry, 1,000. No, that's right. That's right, first time. If I wanted to, I can change this into meters, which would be 0.1 meters, so I have 0.1 over 1. Does not matter. So I can take my inverse sine. What is my angle? What is it? 5.74. Inverse sine of 0.1. So we can now put that value in. And solve for our coefficient of theta, our coefficient of friction alpha. I'm sorry, mu. Good, finish that for tomorrow. Tomorrow we'll come in, we'll just start having some homework for you. So you can start working on tomorrow. So that's all we will be doing tomorrow.